talk about the
I'm ready for 2 o'clock on Saturday.
What's that?
Yeah, tomorrow.
Is anybody competing in the activities tomorrow?
I'm gonna be the snake.
What are you in?
Pizza eating contest.
Pizza eating? I wish I would have seen that earlier.
I'm gonna be the snake.
You wouldn't just see me win.
Huh?
We're playing Quidditch.
Oh, Quidditch. Nice.
I'm gonna be the snake.
That's hilarious.
They're doing it.
Who else is competing? Anybody? Maggie, what are you in?
Each person gets
Every
their own
in that we don't
individually
have
packaged
filled.
pizza.
Really?
Yep.
Are you in? So I got roped in. I'm doing the relay race and the tug of war. I got suckered into doing those.
You never answered my question.
Yes, quickly.
We still have two-legged relay? Two-legged relay?
Huh.
Because me and
Well,
Katie-
I'm eager to see kind of what it's like. Again, reminder, tomorrow. Even today. After this class, go to your second block. So period 4.
Hey, you know that you can watch the live streams of the past homecoming games?
Let's not.
That'd be-
No, let's not.
Oh, let's do it.
No,
Let's do it.
do it.
We're watching film.
No.
You gotta watch this film for next.
Okay, but again, so after this class, go to your 4th period, second block.
No.
Tomorrow, school is normal, except for the very end of the day, your block 4, you will not have class. You go to that class, they'll basically take attendance, and then immediately they'll all go to the football field. Tomorrow is completely normal, but you show up to 4th block just to do attendance, and then you leave. So you won't have 4th block class tomorrow.
So they just changed it again?
No, that's always been the case.
On Friday, the second block. Was supposed to go out there.
That was just today. Yeah, Ish gets swapped with your second block today. So after this class, you'll literally leave and go to your second block, which is going to feel weird, rather than your Ish. Today, so you guys, we've basically covered all the material for this unit. Again, this unit was on dynamics. We did kinematics, which was just motion, right? Now we're on dynamics. We've been looking at forces, Newton's laws. We've been figuring out like how motion happens. So I don't have a ton for you today, but if you can stay with me and stay focused for the first part, we should have some time to hang out at the end. The first thing I want to do is, again, I don't have the ideal lab equipment, otherwise I would have done this as a lab, but I have a simulation of something called a modified Atwood machine that's very pertinent to any type of discussion on dynamics or Newton's laws. So I want us to do that together. Again, if I could have, I would have done it as an entire lab. I want to do that, and then I want to review, or at least start to review for dynamics, this unit. We'll do like a pre-review, and then I'll talk about how we're gonna kind of get ready for the test. What?
We're going to review for the review?
Yes, or do like a high-level review. Then we'll do the full-blown, do some problems review. So anyway, what I want to start with. The other thing, while I have a second, please do not forget what's coming up next Wednesday.
Quarter.
Yeah, that's right. Quarter, right? Grading quarter. So again, I gave you guys that advance notice. Now it's like hey, coming up soon is the end of the grading quarter. That means that all of your grades need to be into me, all your work, missing work, anything, by, right? Wednesday, right? The end of the school day, Wednesday, your grade is done. It is what it is. Really, the important thing is missing work. If you have missing work, get that into me, right? I do not want your grade to be stuck having a big old fat 0 when you can turn it into me and, again, at least get half credit. Most of you, I think, are doing okay. Virtual students, if you've got missing assignments, missing labs, that needs to get into me ASAP. I don't want it to be a scramble, Tuesday night. Get that stuff into me, submit it. I can get it graded. But again, end of the school day on Wednesday, it's done. It is what it is. And I don't want you guys to have your grades suffer because of that. Hi there.
Carol for a quick second.
Yep, no problem. Stop. Gosh, you guys are like the classic, fifth graders in a movie.
Your money's going in the hallway.
Okay, can you guys see this? Let me make this a little bit better. So this, you guys, again, modified Atwood's machine. That's what this is called. As you guys can tell, it's literally a countertop, right? Okay, I'm taking this off. It's a countertop with a pulley hanging off the end of it, right? On that pulley, you have a hanging mass attached to a string that runs over the pulley and is connected to this cart. What you do when you play it, right, you're going to let this go. What's going to happen if I hold this and I let everything go? Tell me what's going to happen. Not a trick question. This way? Yeah, right? Gravity is going to pull this straight down, isn't it? Well, as it pulls it down, it's attached on a string. That string is then going to pull the cart until it hits this stop. Right? What do you know is going to happen? How would you describe that motion? Is it going to be constant motion? Will it speed up? It'll speed up. Why? Why do you know it will speed up? AKA accelerate. How do you know it's not going to just go at a certain speed until it hits the bump stop?
Because the mass of the weight is bigger than the mass of the cart.
Mm-hmm.
And then also it has gravity pulling it down too.
Yeah. Gravity is going to act on this object, isn't it? So if you play this, again, I think it does it fast, which I don't like. That's not too bad. So you see it started to go, and then it picked up speed, right? What happens if let's make a prediction. I added a 0.3 kilogram mass onto the cart. I put weights on top of it. How is the motion going to compare to what we just saw? Be slower, wouldn't it? You got more mass, right? Yeah, definitely slower. Accelerated less. Well, that's because we got more mass. How did we know it would accelerate less if we added mass? What was held constant the whole time? Think of Newton's second law.
The weight of the hanging weight.
Yeah. mg. Right? That we kept that the same for both scenarios. Well, if F equals ma, I'm keeping the force the same. But if I bump up my mass, doesn't my acceleration have to go down? Because I kept the force the exact same. Good. You can also think about it intuitively. It's harder to move a more massive object. And we saw that when I put the mass on there, it moved. It was harder to move. All right, let's go back to what we started with. What if I bump up the hanging mass? What if I have a bigger mass? It's going to accelerate faster. Tell me specifically, why will it go faster? Yep. What specific physics quantity is increasing? You're correct. Think of Newton's second law, F equals ma. What variable are you increasing when you increase this mass? Yes, that is partially true. Think more directly. What causes, force.
Force of gravity.
Sorry, I didn't mean to try and fish an answer out of you, but I wanted you to see if this mass gets bigger, gravity acts stronger. The gravity force is what's acting on this system. Your force increases, even though this is the same. And I need to initialize it. Right? It's hard to tell in the simulation, but it moves faster, doesn't it? So the tricky part that I want to do is I want us to calculate the acceleration. Right? So I want us to do F equals ma. Let's do the start. Oh no, this is fine. F equals ma. These are vectors. Help me out here. What do I start? I got Newton's law. That's a good start.
We got the mass.
We have the mass. What's the mass?
Mass of the thing is 2 kilograms.
What should I write in here?
Could you write both?
Huh?
Could you write both? 1 minus the other.
I don't know.
Be 25.
I'm gonna play dumb right now.
You write the force of F in G. I can't remember what the term is for that.
Force of gravity?
Yeah.
Where?
That
Someone help him out. You guys work together. Don't let Ethan pull all the weight.
It's more fun that way.
Pun intended. But really, I want you guys to think too. Don't.
I'm trying to.
the force of gravity goes on that side.
I can feel it.
And then your mass is.
Okay. Back up a step. Do a free body diagram. That will help us do this. What forces are acting? Tell me what to draw. Gravity on what?
On the block.
50 kilograms.
Right here?
All right.
I just opened a brand new black Expo, and it writes like a dream.
Oh yeah.
Oh yeah,
Oh yeah.
that's nice. So this is force of gravity. What other forces are acting?
On the block, not.
We agree with Ethan?
Friction.
Well, we have the friction set to 0.
Good point, but we've set the coefficients. We're assuming friction isn't a thing, doesn't affect it. We're going to make it simple. What other forces are acting?
Would the force of the cart be slowing it down? So in the upward direction?
Does gravity act on the cart?
No. Well, yeah, it does. The normal force cancels that out. The normal force is cancel out.
So you said two forces. Shouldn't we draw that on our free body diagram?
Probably, yeah.
Yeah. You said there's gravity, right?
Yeah.
And you said it's what? It's balanced out with what?
The normal force.
Normal force.
And then there's no normal force on the block because
Yeah.
it's in free fall.
However, if I pin this cart down, does my block fall?
No.
According to our free body diagram, it would.
So our normal force is both of them.
This is correct for the cart.
The string that attaches it.
The string.
So the string is the normal.
Remember we talked about tension? F tension.
Gotcha.
It gets weird. This is connecting a lot of dots for us. We're using Newton's second law. We're using free body diagrams and just general force analysis. We're also bringing in different types of forces. And the idea, remember when I was talking about the system? Remember when we had that horse buggy, right? The system is what you're like analyzing. Yeah. In this what is our system here?
The cart and the block connected.
Yes, I have a cart, I have a block, and a string. Right? If I play this, what is in motion? Cart, block, string. That is my system. So I need to think of that entire system. Right? Gravity acts on my cart, which is a part of my system. Gravity also acts on a different part of my system. So I have two forces of gravity on my system. One normal force acting on the system. And then, technically, this you would only draw if you cut the system in half, right? If the string is a part of my system, my string can't act on itself, right? This is only correct if I cut the string. Well, if I do that, now I have a tension force here, don't I? If I only look at the cart, well, this string pulls on it. The string's not a part of my system anymore. Well, now I have two separate problems, right? In this situation, what's the force of gravity? Calculate it. Or just tell me the equation. So it was mg, right?
0.5 times.
Gravity is mg. Half kilogram block. Gravity is 9.8. You can round up to 10, whatever, but 4.9 newtons of gravity. And then we got this tension force. These cancel out, right? Correct? It doesn't move up and down on the table, right? So the gravity pushing it through the table is supported by the table. This is irrelevant. We don't care. It's just going to be this equals this. Well, that's a pointless equation. But we do know that there is one tension force, right? There's no friction. So for the cart, whatever motion happens is caused by the tension force. So we need to write two equations. This one is going to be for the cart. Over here, we're going to do the block. This we know is, that we know for sure. But we don't really know tension because we don't know the exact acceleration of that block. We would need to do F equals ma. Well, we don't know this tension, so we don't know this one, and we don't know this object's acceleration. We don't know how quickly that cart is accelerating. So let's do Newton's second law for both of them. All right, we're going to cut this system in half and look at each part individually. We're only looking in the x direction, so what is the force acting in the x direction on the cart? Tell me from the free body diagram. Force of tension. Right? Good deal. These cancel out, and that's in the y direction. We're going here. I only see one force. The sum of the forces in that direction, just tension. I leave it as a positive, right? To the right is always my positive x direction. What's the mass of that cart? Yes, I'm gonna leave it symbolic right now. Ethan's right, it's 0.25. I'm gonna leave it as this capital M. What's the acceleration? We don't know it, do we? we can't say for sure what it is. So we have to leave this as an unknown. So really, we only have one known. Well, crap. Can't do anything. Well, let's go to something else. Can we do anything with this? What is the motion? What direction is the motion happening?
Down.
Up and down. Now we're looking in the y direction. Do we know that acceleration? No, we don't.
Oh, yeah. MC gravity.
Yeah, we don't know for sure. We want to say, hey, it's 9.8. We don't actually know that. If we solve this and it tells us 9.8, Newton's second law would confirm us. The mass of the cart, we know, it's little m. I'm going to leave it as a symbol right now. How about the force? I wrote Newton's second law improperly. I need the sum. Well, what forces are acting in the y direction here? Gravity and tension. Isn't it the rope trying to pull up on it? It resists motion. So if this is positive, I need to write it like that, don't I? F tension is in the positive y direction. F gravity is in the negative y direction.
We still have to work.
Yeah, we know this, but we don't know tension. Well, what the heck are we supposed to do?
I know it's good. I'm doing something I can't figure out. Give up.
That's the spirit. They have two unknowns here and two unknowns here. Do you see any similarities?
It's the same two things.
Huh?
It's the force of tension
And the force of tension. Can we write these together? Can you solve a system of equations and solve for two unknowns with two equations? We're going to do some algebra. What do we know is true about this force of tension and that force of tension? Yeah. John said they're the same tension. It's the same string. However hard I pull with the block, it will pull on the cart. If the cart pulls back, that pull is the same on the block. Yes, quickly. Yes. This is super important as long as you understand this. Oh, yes. Thank you. Appreciate you reminding me. So now we have two equations, two unknowns. There's actually two ways we can solve this. Yeah, so what we could do, I'm trying to think of which one I want to do.
I heard the diffusion. The Atwood gave another one. I don't remember what it's called. But another way.
Okay, I'm going to skip a step and ask you to think about this like from a high-level conceptual view. You guys told me that tension force in both equations, that's actually the same force. So whatever I solve for here, I should be able to plug in over there, right? It's the same string, I'm just cutting it, and it's acting on the two ends. So this Ft is the same on the block and the cart. Can we compare the accelerations of both objects? Think about the motion. Watch them.
I mean, you said the same way. Because the string's connected to the rest of the system.
What can you say about the acceleration of the cart and the acceleration of the block?
They're the same. Because
What evidence do you have that they're the same?
the tension of the string is always at full tension, so it moves the same distance. So
I like that logic. He said they're always moving the same distance. Think about it. I'm going to foolproof your reasoning because Ethan said they move the same distance every time. Can I pull this block down? Can I move the block without moving the cart? No. If I hold that block and I would say, I want to move it down a little bit, but don't tell the cart because I don't want it to move. The cart is going to move. It's literally connected by a string. If I pull this down 1 inch, guess what happens to the cart? It gets pulled 1 inch. So what can you say about the acceleration of both objects? It's the same. So the force of tension, those are identical. The accelerations also are identical. So technically I should have written this as acceleration cart, acceleration block, and then you'd be like, oh crap, I got AC and AB. Well, if you think about it like we just concluded, you're like, AC and AB are equal to each other. So I can say, that's the same variable. I got 2 equations and 2 unknowns that are the same variable. I can solve it now. So, which one do you want to plug in and solve for? Do you want to take FT and plug it in here? Or do you want to rearrange for acceleration and plug it in here?
I think since FT is already solved, we can do that.
All right. So we said on this side, the force of tension is big A, or big M A. So I'm going to do big M A minus FG equals. What's the force of gravity? Yeah, I'm going to leave it as a math, like. Do we agree with that? Force of gravity on the block is mg. The mass of the block, little m, times 9.8. So I'm going to actually get rid of this. I don't want you to. This, from was that other equation, that was the mass of the cart, right? Don't I have A on both sides? So don't I want to take negative mg equals ma minus ma? I just did algebra. Do you agree with me? I want to put the a's on the same side. Agree? So I just subtracted big M A over to the other side. Well, I don't really want this negative. Can I pull the acceleration out and say m right? I want to solve for A. That's my unknown right now. So I'm going to say over
Mass of gravity is 4.9, and then that is 0.25.
So you said, now we can plug in 0.5 times 9.8.
Over
What was big M? 0.25?
9.05.
It should be flipped around. I hope I didn't do our math wrong. Where did I do my math wrong? Haha, dang it. I did do my math wrong. Does anybody see where I did it wrong? I feel like a dummy. See? Everyone's fallible. I told you guys before, do not treat me like a magic source of knowledge. I'm a human being. Don't ask me what the answer is and then take my word for it. I messed up here. What did I mess up with this equation? I messed up with the direction. My variables are right, but the directions are wrong. I said tension is up, gravity is down. Acceleration is down. I flipped my signs. If this is a positive A, like I said it was, this is the positive direction. I wrote my equation wrong. If this is my positive direction, this is negative. That's positive. Or I need to put the negative sign here. Right? Your convention you have to stick with for everything. It's a great catch. This, if I'm going to say, hey, it accelerates downward, and I'm going to just leave it as a positive A, that's fine. But that means FG is positive, and that's negative. One thing that I think is more intuitive, right? We always think like, oh, this is positive. Let's go with that, but fix my equation. Tension is positive. Up is positive. We like that. Down is negative. This is correct, but I need to put a negative sign here. Because this is negative A. So this becomes negative MA. Right? I knew what the answer should have been. That's how I knew I did something wrong. You could have also done your math. What did you calculate for the acceleration, Ethan? 19.6. 19.6?
It's very high.
Does that make sense?
It looked really weird to me.
If I put a block and attach it to a string, to a cart, and I let it go, it accelerates faster than gravity?
Yeah, that makes sense, right?
That don't make sense. That's another thing that I want to encourage you guys. Always gut check your answer. Right? If you get like 5 billion newtons in your math, and you're like, I'm calculating the force that an apple hits the ground. That doesn't seem right. It's probably because it's not.
Apple falls off the table, goes to
Yeah, splits the earth. When we did this, Ethan, if we'd have done the math, Ethan said 19. Well, that should have triggered you like,
I did. I said, wait a minute, shouldn't that be flipped?
yes, that's your gut check. Like, that don't sound right. That doesn't make sense. That can often save you. Mistakes like I made. So now I can do my math, and it's going to tell me the answer that I want. I just repeat my process. FT is MA. So I'm going to do, here, what did I say? MA minus FG is minus MA. Right? I want the A's on both sides, so I'm going to do minus FG equals negative MA minus big M A. You agree with my math? I don't want to make a second mistake. Subtract that to the other side. Well, I got a bunch of minuses. I can get rid of those. If I multiply both sides by -1. Now I want to solve for A. Well, I can say, what's FG equal to? What's, yep, mg, right? M times G equals, I'll pull my A out, and I got little m plus big M. Now I want to solve for A. That's the unknown variable that I have left. I can plug in this, plug in this, plug in this, plug in this. Mg over right? Now I have, this is what I want. So do my math, right? 0.5 times 9.8. 0.5 for the cart, or the mass, plus 0.25. Right, sorry. Do we agree with that? Little m is 0.5, g is 9.8. Little m is 0.5, big M, ironically, is 0.25. Well, what's that come out to?
Negative,
The 0.75?
You have it 0.5 plus 0.5 plus 0.5.
Oh, no, the whole fraction.
Oh, the whole fraction, all right.
Yeah, can someone do that math for me? So basically, 4.9 divided by 0.75.
6.53.
No, what did you say, 6.53?
Yep, 6.53 repeated. 1.3, yeah.
Bam. That is the acceleration of the block. That's the acceleration of the cart. And the acceleration of the cart block system. Do you see how it is less than gravity?
Yes.
Intuitively check that. This does not fall in free fall, which would be 9.8. There's a string that resists its motion, so it doesn't accelerate as much. That resistance is this chunk of cart that it's got to pull. It's trying to fall. It can't do it completely because it's got to drag this cart. That should make sense, because if I drop this or I leave it on the string, isn't my force the same? Right? If I drop it, the force is 9.8, or mg. If I attach a string to it, now I have this whole system. The only force on the system is still mg. Don't I have more mass now? I gotta lug the block and the cart. That should make sense that the same force can't do as much. So it accelerates more slowly because I have two masses to move with that same force. Another thing I want you to point out. See this? This was our final conclusion. I'm gonna erase everything. I hope you guys, like, this is, when I learned this, I was like, what? Now let's do not the cart or the block, let's do them together. Cart and block. Think Newton's second law still works? Probably does. Let's see. F equals ma. I'm going to do S. Now I'm looking at the entire system. Easy part. What is the mass of my system? The cart, the string, and the block. Yeah. I got big M plus little m. The acceleration of my system, I don't know. What forces are acting on the system? I got this, don't I? Do I have another gravity? Block, cart.
Natural force, right?
What?
Natural force.
Normal force.
Normal
But
force.
yes, yep. Good. The table's supporting that. Any other forces acting on my system? No. Notice I don't put tension. That rope is a part of my system. My rope can't apply a force on the rope. It's included. I don't care what happens inside my system. Josh?
Isn't that block that stops it, would that be a force?
Yes, but we want to consider from when I let it go to the moment before it hits there. So when it's in motion, what's acting. So we don't include that. This is all I got, right?
Would there be any force going against it?
Like friction, you mean?
Yeah.
No. And we simplified and said, hey, no friction.
Oh.
We're going to assume frictionless. This is all I got, don't I? It's all in the y direction. Technically, I would write force normal. Actually, I would write force gravity plus this minus this. If we say this accelerates positive. Or, if I say, hey, that's accelerating in the negative direction, that's negative, negative, positive. What do these two do? Yeah. So technically I would write, I'm going to include a negative. We're going to keep our sign convention. Down is negative. So I would say Fn minus FGC minus FGB. Well, you just told me the normal force and this gravity force equal opposite, they cancel out. Minus, well, if I, oh, wait, I wrote that wrong. I need to put my negative sign out front. Times, if I add the opposite, solve for acceleration. Oops, I did my math wrong. You see some sort of similarity?
Whoa.
You see that? If we did Newton's second law for each block or each piece, and we said, hey, there's some connection. I'm going to put them together and I can solve it because they're connected. Or you could have just looked at the entire thing and applied Newton's second law to the entire thing. Lo and behold, they're the same answer. Yeah. Maybe you're not as wowed as I was. And this makes a lot of sense. That's pretty good. This makes sense. The only force acting is the gravity on the block. It's the only thing moving the system. The system has a mass of this plus this, total. Well, then I want the acceleration. It's literally F equals ma. Over here, we went the long way and figured out the conclusion for the acceleration of both blocks when you do the math and actually bring them together is it's that force divided by that mass is the acceleration. They're the exact same thing. Now, if I were to ask you, hey, calculate the acceleration of this system, you guys would say F equals ma. You just say this force of gravity moves the cart at whatever acceleration. But then you forget, well, what about this mass? How does it move down to move the cart? They're linked. You have to include it. The one force has to move both masses. Most people will get this wrong the first time they're asked if they haven't seen it. Because they forget that block has a mass too. You can't just ignore that somehow a piece of mass is in motion. Well, you got to take that into account by including it in Newton's second law. Does that make sense? Again, I was going to do this as a lab for you guys. And I almost guarantee you all would have gotten it wrong, or most likely. And then I would have had to come back and kind of connect the dots. No, it's like everybody. Like anybody on the street won't be able to get this. They'll almost always forget it. That's why the modified Atwood machine, it's such a famous thing. Like you can Google all sorts of stuff about it because it's such a big, like, conceptual misunderstanding in physics. And it really comes down to like defining your system. Two things are an object or in motion and they're connected. I have to include both of them in order to consider the motion of the system. Yes, yeah, you can. Any questions about that? I wanted to go through it with you. I'm kind of glad that I made a mistake. Again, to reaffirm, I am not the gatekeeper of physics knowledge.
You're not.
Why not?
Then who should I go to?
Nobody. You should go to your own stinking brain. So same thing. Even if you never go into science, you are going to be a voting citizen, right? We got an election coming up. Did anybody watch the debate?
Oh, I didn't because I heard it was awful.
Garbage fire.
It was terrible.
Garbage fire.
I'm biased.
Dumpster fire, as my friends call it.
It was terrible.
It was
Everybody
awful.
was.
I hate politics. Hardly ever watch debates. I'm not as great of a civic citizen as I should be. But I did watch it. My wife is very political, like very up to date, watches the news. And she's like, can we watch it? I missed it. I was like, okay. I was like 5 minutes in. And I was like, this sucks.
That debate was terrible.
This is terrible. My point is, back to science. They're talking about COVID. COVID is very much, there's politics, of course. It's also very scientific, right? So we don't just believe, we shouldn't believe something that a scientist says. Why? If they're a scientist, why should I not believe them? If they just say something.
They might have done something wrong.
Andre nailed it. Where is their evidence? Science literally doesn't exist without evidence. It's like a fundamental principle of what science is you make a claim with evidence to support that claim. You cannot say something in that. My chemistry classes, they guess on the answer, and I tell them they're wrong. And then when I tell them the answer, like, I said that. It's like, you didn't give me any evidence. You just said an answer. That's garbage in science. Then, again, don't say, look at my work and be like, oh, Mr. E, copy that down. I made a mistake. I'm not a magic gatekeeper of science knowledge. I can't overestimate like how important that is, not only to AP, this class, right? Good experimental design is you come up with some conclusion at the end based on the evidence you just found. And AP will test you on that. You're right, make a claim based on evidence. But also in general, I can be wrong. Don't take my word as 100%. Now, I know a lot of physics, right? There's a good chance I've done the work. Huh?
Where's the evidence?
I'll show you my degrees,
Okay.
plural. Just toot my own
That's
horn
why
a
you're
little
also
bit.
here.
What?
That's why you're also here.
Yeah.
Weird flex, but okay.
I took my degrees out. I had them in my cupboard. I could show you right now. But again, challenge me sometimes. If I say something like, oh, F equals MA, like, feel free to say, like, how do we know that's true? Well, let's look some stuff up, right? Do some problems. We can get some measurements. Or if I say, the friction force is always, the static friction force is always larger than the kinetic friction force, at least the P. You can be like, how do we know that? And I can show you equations, we can look up data, we can look up experiments, get some evidence to say, oh yeah, I believe that now. I believe Mr. H. Anyway, I'm done tirading about evidence. This is something that is very connected to all these pieces, right? Newton's second law. What do we define as the system, right? Free body diagrams, forces, coordinate systems, right? What's up, what's down, what's positive, what's negative. Don't forget that, because I did and screwed the whole thing up, right? So any questions about the modified Atwoods? Okay. What I think I want to do now, can you guys get out your, I'm going to kind of make this up a little bit. Can you guys get out your Chromebooks? I want to look at, there's a big ideas sheet that I put on the classroom. I want you to get that out. I'm going to go through it with you, but, oh, where was it?
Sit down.
Brody.
I need to charge my computer. I have my charger.
Just sit out for now. I'll pull it up on the screen for you guys. I want you to get it out if you have it. But what I want you to be aware of is it's in your classroom. Actually, let me go to yours. That was the virtual students, but it's in yours. It's at the very bottom. I put this big ideas document. This should be something I want you guys to keep coming back to. This is a list of the big ideas broken down by unit. So if we look back at the unit we just finished, there's all of these like big statements that says, hey, the average velocity is the change in position divided by the change in time. It's basically a summary of the key concepts that we learn in each unit. So I want to direct your attention, and I want to talk about, in dynamics, I want to go through and reiterate and reinforce and see if you have questions about these key concepts, these big ideas for this unit on dynamics, which is looking at motion and the forces that cause the motion. Newton's laws, right? First one, inertia is a property of all matter. Matter resists changes in motion, aka acceleration. That is Newton's first law. Do you remember that? Aiden, what's Newton's first law?
An object in motion stays in motion unless acted upon by an outside force.
Bingo. Good work. The follow-up is an object at rest remains at rest unless acted upon by outside force. But Aiden's got it. That's what inertia is. Do you remember talking about that?
Yes.
The more mass an object has, therefore the more inertia it has. The more inertia it has, the harder it is to move. That's back to my car example. Car crash. Who's better off? The smart car at 40 mile an hour or the Suburban at 40 mile an hour? The Suburban.
It's me.
It has more inertia. It experiences less acceleration. Right? Acceleration is proportional to the net force. This is literally F equals ma. Right? They write it kind of small, but acceleration is the acceleration of something inversely proportional to its mass. The more mass something has, the less it accelerates. The less mass you have, the more acceleration it has. Literally, it's just algebra, right? If I make this number bigger, it makes my fraction smaller, aka this is smaller. That was Newton's second law, F equals ma. Mass is a measure of how much matter there is, and it's directly proportional to inertia. Right? The definition, gosh, my shoes are squeaky. Mass is just how many atoms are in an object. Right? That's the fundamental definition of what mass is. how much matter you have. Matter or mass and inertia, they're different, but they're synonymous. They're directly proportional. If I have more matter in an object, I have more inertia. What units do we measure mass in? Science class. No.
Grams.
Kilograms.
Oh, I'll do
How do we measure force?
Newtons.
Newtons. What do we measure acceleration in?
Meters per second squared.
Meters per second squared. Good. Two objects of different weights will accelerate at the same rate because the object with more force has more mass. Does this statement make sense? This goes back to the bowling ball feather. They have different weights, correct? A bowling ball weighs more than a couple feathers. Let's do even one feather. Right? But if you drop them again in a vacuum and say, hey, if we just see what gravity does on both those objects, how do they fall compared to each other?
Same speed.
The same. It's weird because when we would see that, we see air resistance that changes it completely. But if you just have gravity, gravity causes the same acceleration on two objects that have completely different masses. Well, why is that? The force of gravity on the bowling ball is mg. The force of gravity on the feather is mg. Right?
Force times.
If my force on the bowling ball is mg, force on my feather is mg. These cancel out. The acceleration is gravity. Acceleration is gravity. They accelerate the same, even though they have different masses, they have different forces. There's more gravity on the bowling ball, but more mass, so it doesn't change anything. There's less mass in the feather, aka less gravity force, but there's less mass, so it's still g. Again, we are ignoring air resistance in that situation, which would be an additional force that you'd have to consider. Acceleration is the ratio of force per mass, F over m. Weight is the force of gravity, right? I should never, and catch me on this, I should never say that bowling ball weighs 5 kilograms. That's scientific gibberish. I just said that bowling ball has a force of 5 kilograms. Kilograms is mass. That's completely different. So I'm going to try and be careful and say the mass, go mass that object. That means tell me how many grams or kilograms it is. If I tell you to go weigh it, you should figure out newtons. Weight is a force. We use it weird in the U.S., and that's why it's so confusing for American physics or science students. In this class, we measure force in newtons. Weight is mass times mass times the acceleration of gravity. Fg is the weight of something. It's equal to mass times the acceleration rate of gravity. This mg is essentially the field strength of gravity. It's just mg. So the strength of gravity on an object is just mg. Acceleration is in the same direction as the net force. Go back to Newton's second law. Did I write Newton's second law correctly? Huh? Vectors. Mass is not a vector. It's a scalar. It's just a number. Force and acceleration are vectors. Can I ever have the force and the acceleration be in opposite directions? The total. No. I can't have a force go this way and an acceleration go that way. That would basically mean like positives and negatives could equal each other somehow. What else am I missing on my F equals ma equation? Yeah. So we'll say y. Missing something else. Is it just the one force in the y direction?
Oh, the
Sigma. All the forces in one direction that act on an object, whatever the net force is, the remaining force, that causes motion. If I have a book on a table, gravity pulls it down, but the table supports it. I don't do Fg equals ma. I got to do Fg, or F normal minus Fg. Those go to 0. Then I can say, hey, no force, so no acceleration. So this is talking about the direction of vectors. Force and acceleration are vectors. If I push on an object, the acceleration is in the same direction. That should also make sense intuitively, right? If I push a book, its motion changes in the direction that I'm pushing. Acceleration 0 when net force 0. That's what I just said. If you have two forces, that doesn't always mean there's motion. They're equal and opposite. They go to 0. The only time you can have no acceleration is if you have no net force. That's Newton's first law. I don't care if an object's going a billion miles an hour. It will not change that speed until you have some net force. If it's stuck on a table, that will never ever move until some net force acts on it to cause an acceleration. Equilibrium when the net force is 0. Equilibrium is that fancy term for all the forces are equal, it's not doing anything. That's equilibrium. Acceleration is 0 does not imply 0 velocity. That was the example I just gave. If you're going in the interstate and you got cruise control at 70, are you accelerating? No. Your velocity is not changing. I'm not speeding up or slowing down. So do you have any net force on your car? No. Right? Your engine is turning the wheels and friction opposes it and pushes you forward. Now you have air resistance. The air resistance and the friction of your tires pushing you forward, they're balanced. That's why you're stuck at 70 miles an hour. When you stomp on the gas, more force in your friction pushing you forward. Now you have a net force, then you can speed up. So that's why even though you might have a velocity, if it's not changing, there's no net force. Acceleration 0 means the velocity is not changing. It's the opposite. If you know that there is 0 acceleration, whatever speed you're at, it's stuck there. Whether that's 0 or 2,000 meters per second. Force is a vector. They can be added like head to tail, right? That's where we're talking about our breaking up components. Or if you have two vectors in the same direction, you can add them up because they're both going in the same direction. We can always break them into components. This is the x and y directions. We need to sum the forces in the x direction, sum the forces in the y direction, and do Newton's law in both directions. Newton's third law. Every action, there's an equal and opposite reaction, right? When we kick a soccer ball versus kicking a bowling ball, which one hurts more? The bowling ball, of course. Well, whatever force I can apply, say I kick at the same force, which one can resist my force more? The bowling ball. It's got more inertia.
Wait.
Huh.
What if?
Oh boy.
If you kick the bowling ball so hard, it breaks everything in your foot, and you don't feel it. Because if it breaks everything, where are you going to
Would there be like a specific threshold where you could hit it so hard that you don't feel it?
I don't know.
Probably feel it more, but
I feel like that gets into like
Destroy your entire nervous
advanced
system in your
like neurobiology.
Probably, yeah.
Because feeling only comes from like your nerves.
Yeah.
But
So
if
do
you
you,
break those,
you're
nerves,
able to
it's
destroy your
hard,
entire
you
nervous
destroy the
system.
nerves.
You got it.
Can you hit it hard enough? Oh yeah, you can hit it hard enough that it breaks because it can't resist enough.
You could. See, this is cool though. This is like biomedical engineering.
This reminds me of like the
Like-
how hard would it have to stop a chicken for it to be able to cook it?
Yeah. XKCD or X, I never know it. They actually do the math on that. Is that the article you're talking about? It's XKCD. That's one of my favorite sites because he does like absurd physics questions and he literally does the math. Like how much energy does a slab have? Well, how much energy does it take to cook it? Do the math and it's like, 1 million slaps to like put enough energy to cook a chicken. Something ridiculous.
But you can't slap a chicken 1 million times and cook
In a certain amount, yes. Anyway, I'll try and find some of those. On the momentum ones, I have a couple queued up. But anyway, okay, I want to get through these.
Have to stop the chicken with 3,000
Spring pushes or pulls directly proportional to displacement.
miles per hour.
Remember Hooke's law?
Per hand.
The spring force is equal to kx. If I push the spring, I apply a force on the spring. Does the spring push back on me? Yes. It always wants to go to its natural length. If I push it this way, it wants to go back to its natural length, so it pushes equal and opposite. K is the stiffness of the spring. A large K means you have to put a ton of force to compress it a certain distance. Right? Direction of force is always opposite the displacement. Whatever I push the spring, it wants to do the opposite. It wants to go back to where it started. The spring constant is force per displacement. If it takes 100 newtons to compress it a meter, your K value is 100 newtons per meter. It's the stiffness. Coefficient of friction. Remember? It basically tells you how grippy things are. Static friction always is equal and opposite to the force applied. Right? The static friction is what you have to overcome in order for motion to start. What happens when I exceed the static friction limit? If I push it, friction is resisting and then it slips, what happens to my friction force? It starts moving. Now I'm in kinetic friction. Is kinetic friction larger or smaller than static?
Small.
Smaller. It dips a little bit, and then static friction is constant no matter what kind of motion you're in. Right? Remember that graph that I showed you?
So then when you stop...
Friction, and...
Yeah, so then when it stops moving, does its kinetic friction just immediately drop to zero? Like you start pushing it, and it doesn't go, and then you get to start pushing it, and it starts moving, and then you stop it, does its static friction, or its kinetic friction just drop straight to zero?
Do you slowly stop? Do you decrease your force slowly?
I don't know.
I mean, if you start to let off, eventually the static friction will kick in and it'll spike up, and then it stops.
Yeah, okay.
Because you've gotten less than the static, less than the kinetic, and so it switches back.
Okay.
Yeah, it depends on how you're changing the force. Yeah. Kinetic friction is what you have to overcome to keep it in motion, right? To keep it sliding, you have to overcome kinetic friction. The mu value, mu k or mu s, is dependent on the materials. It's the interaction of those two surfaces in friction. It tells you how grippy they are, right? Metal on ice has a lower coefficient of friction than metal on rubber. Metal and rubber grips more. You have stronger friction. And then all friction, whether it's static or kinetic, what's the equation? What does it depend on? Normal force. To calculate friction, the friction force is equal to the coefficient of friction times normal force. What that means is basically how strongly is that object pressed together, right? It depends on the materials and how strong you push down. That's why you sandbag your car in the winter. You want more weight pushing on the wheels to create more normal force to give you better friction. I can't change the rubber on my tire. It's rubber on ice. The only thing I can change is the normal force.
Or you can put spikes in.
You could. That would change the coefficient. That works. If you use winter tires, they use a different rubber that's softer and grips better. You change your coefficient to get more friction. You could also add a sandbag to improve the normal force as well. You boost both of them so you get better friction. And coefficient of static friction, always greater than the coefficient of kinetic. Well, that's because static friction is higher, and then it dips a bit to go to your kinetic. All right? Hopefully that made sense. I know I went through a lot, but it's just review of all these little pieces. I want you guys to, again, I'm not going to do the free response checks for your test, right? I'm not going to do that. What I think I am going to do is I'm going to assign them as just practice, right? One, to continue to practice AP questions. My tests, I'm going to make a test for you this unit based on what we need to, right? More or less, these big ideas, hint, hint. This list will be very helpful. It's a very good summary of these big concepts that we need to know and understand. I'm going to pull a lot of questions from, we need to know about friction. Well, I'm going to ask them a question to see if they understand that static friction is bigger than kinetic, right? Things like that. Anyway, review this over the weekend. I think what we're going to do, we would come back Monday and see you guys. I think we're going to review finally, right? I'm going to try and make a review sheet so that we can do problems. And I'm going to spend the class, right? I have an extra day built in where I can take all of Monday for us to review. I'm going to try to bring problems for you guys to solve, essentially a practice test that we can focus on. Now, over the weekend, what I want you to do, I think I'll assign the first progress check. It's not graded. I just need you to do it as best you can. Use it as a very early pretest, right? Try to study and then take that progress check to see how well you do. I'll have it release the answers immediately so that you can check right away. We can go over some of them if you want. And then in class Monday, we'll actually do like some problem-solving review, not conceptual review, to get you ready for the test, which would then be Wednesday. Does that sound good?
So when we take the progress check?
I'll assign it like over the weekend. So do it before you see me next on Monday. So anytime this weekend. I think it's like 20 questions. Again, it's not graded. Don't freak out about it, but do the best that you can, right? It's pointless for you to like half attempt a practice because then you don't have an actual understanding of like what you know and don't know. Any other questions? Again, don't forget, Wednesday is the end of the grading quarter, right? Your test will probably go on the second quarter.
Good call.
Yeah, I don't think I can grade them that fast. Within the hour.
I got another class to worry about.
Like you get to like 5 or something.
Yeah, it technically might be.
Yeah.
But I think,
You stop accepting stuff.
yeah, and technically, if it happens on Wednesday, it could go in the grade book, but I won't be able to. We'll see. It doesn't matter for you guys. It doesn't matter. Any other questions?
We done?
Yes, I didn't give you as much time as I thought. Dang it. Sorry. I did want to take time to go over these big ideas because, oh good, I played that.